Precision forging and machining transform iron and steel into high-performance components, combining craftsmanship, advanced techniques, and industrial expertise. The production of the rope used on the Pisval Grande E5 gondola begins at Fatzer AG, where fully locked coil cables are engineered to meet precise strength, diameter, and weight requirements. The 72 mm track rope is built from multiple strands arranged in several layers, with each layer added in a separate, closely monitored twisting step. Modern ropes integrate not only high-strength steel wires, but also embedded electrical conductors and fiber optic lines for power and data transmission. These customized cables, designed for increasing cabin sizes and speeds, achieve service lives of up to 40 years. The flash butt welding machine, DDIFB180X4Z, with DCU30 control, is designed for joining chains, bars, rings, and flat bars with high voltage and high current. It performs precise flash butt welding, ensuring strong, consistent joints while minimizing deformation. However, welding may create sharp or uneven edges, so the integrated deburring unit immediately removes burrs to deliver smooth, safe, and high-quality products. By combining welding and deburring in one coordinated system, manufacturers achieve stable parameters, reduced defects, and improved overall production quality. The BSM 250RROR cage welding machine is a highly efficient system designed for producing reinforcement cages used in manholes and concrete pipes. Built for precision and productivity, the machine automates the entire cage forming process, ensuring consistent dimensional accuracy and superior weld quality. Its most distinctive feature is the patented round-oval-round reinforcement production method. This innovative concept allows the machine to reshape the cage geometry during manufacturing, creating an optimized structure that maintains strength while reducing unnecessary steel usage. By adapting the cage form to match load and flow requirements, the ROR system can provide up to 50% savings in reinforcement material and overall operating costs. Throughout production, the machine synchronizes wire feeding, rotation, and welding to deliver uniform spacing and firm connections between longitudinal bars and spiral wires. This not only enhances structural performance, but also minimizes manual labor. The BSM 250RROR is engineered for continuous, reliable operation in industrial environments. Its automated controls, robust frame, and precise welding technology make it ideal for high-volume reinforcement manufacturing. As a result, concrete pipe and manhole producers benefit from reduced material consumption, increased efficiency, and consistently high-quality cages tailored to modern construction standards. The machining of a Toyota crankshaft from a 140 mm diameter ultra-clean billet showcases a highly controlled and fully integrated manufacturing sequence. The process begins with selecting a vacuum arc remelted high-tensile alloy, ensuring exceptional purity and structural integrity. The billet is loaded into a Mori Seiki multi-axis tasking machine, where the entire crankshaft is produced in a single setup to maintain perfect concentricity and squareness. First, the main bearing journals are turned to establish the primary reference surfaces. The big end journals are then multi-axis milled, allowing precise formation of the offset crank pins. Rough machining is carried out on the counterweights to remove bulk material, followed by precision machining to achieve accurate geometry and optimized mass distribution. Once the big end journals reach their near final form, The finishing passes are applied to refine their dimensions and surface quality. A critical stage involves balance machining, where material is selectively removed to harmonize the counterweights with the crank throws. Final concentric turning is performed to eliminate any stress variations caused by earlier milling operations. Oil gallery drilling is completed next, including both the main journal galleries and the cross-drilled passages that supply lubrication to the big end bearings. Afterward, the crankshaft is parted off from the billet. Heat treatment is performed by RJ heat treatment, where the component is through hardened, tempered, cryogenically treated, shot peened, and polished to enhance strength and fatigue resistance. The final precision grinding of the journals uses a cylindrical grinding process, bringing each surface to exact tolerances and completing the high-accuracy crankshaft ready for engine assembly. The Danobat DPL portal lathe is a highly specialized CNC machine engineered for the precise maintenance of railway wheel sets. Designed as a roll-through portal system, it allows individual wheel sets from locomotives, coaches, and wagons to be reprofiled efficiently without extensive manual handling. Its primary purpose is to restore wheel geometry and machine brake discs, ensuring that rolling stock operates safely and smoothly on the track. At the core of the machine is a robust, full cast iron structure that provides exceptional rigidity, vibration damping, and long-term dimensional stability. This heavy, thermally stable construction enables the lathe to maintain accuracy even under demanding industrial conditions and significant temperature variations. The DPL lathe is built to withstand high static and dynamic loads, making it suitable for intensive maintenance environments in railway depots and workshops. The machine is equipped with two hydraulically actuated tailstocks featuring a mechanical blocking system that guarantees secure clamping and precise alignment of the wheel set during turning. To support continuous operation, an integrated swarf crusher and conveyor efficiently manage chips and debris generated during machining. Overall, the Danobat DPL portal lathe delivers high throughput, consistent precision, and reliable performance, making it a key solution for modern railway wheelset maintenance and lifecycle management. The machining process on the quick-turn 250 MSY, equipped with the TA-2270th automation system, demonstrates a highly integrated and flexible manufacturing sequence tailored for modern production demands. This advanced turning center combines turning, milling, Y-axis machining, and dual spindle operation into one seamless workflow. As the cycle begins, the TA-2270th robot utilizes its double gripper hand to simultaneously unload a finished workpiece and load a new raw blank. This dual-action capability significantly reduces non-cutting time and ensures continuous spindle utilization, which is essential for high-throughput environments. Once the stock is securely clamped in the main spindle, the machine executes the programmed operations through either Mazatral conversational programming or traditional EIA/ISO G code. Mazatral's intuitive interface streamlines setup, while G code ensures compatibility with offline programming and complex toolpaths. The machining sequence typically starts with rough turning to remove the bulk material, followed by precision finishing cuts to achieve the required diameters and surface qualities. Because the machine includes a y-axis, it can perform high-feed milling operations directly on the turning center. The x and y-axes support dynamic milling strategies that dramatically reduce cycle time, especially when machining pockets, flats, or complex geometry on the workpiece's outer surface. Additionally, the machine's rigid structure allows full contour milling using the c-axis, enabling the spindle to position and interpolate smoothly for circular or helical features. This capability eliminates the need to transfer the part to a separate machining center, thus improving efficiency and accuracy. One of the distinctive features of the process is the production of internal splines using a reciprocating broaching tool. This method allows the machine to generate spline profiles with high precision using controlled linear oscillation. The integration of this broaching capability within the lathe further consolidates processes and reduces the need for specialized external equipment. After the first spindle operations are complete, the workpiece is handed off automatically to the second spindle. The seamless transfer performed without operator intervention maintains perfect concentricity between all machined features. The second spindle then completes backside operations such as facing, drilling, tapping, or milling features that require full contouring via the C2 axis. This dual spindle architecture ensures all sides of the part are machined in one continuous cycle, minimizing handling time and eliminating potential misalignment. Throughout the process, the TA-2270th automation system synchronizes precisely with the machine's cycle. As the second spindle finishes the part and releases it, the robot immediately retrieves it while preparing the next blank, maintaining a constant workflow. This high level of automation not only increases productivity, but also enhances consistency and repeatability across large production batches. In summary, the quick turn with TA-2270th automation represents a fully integrated, multitasking production cell capable of turning, milling, y-axis machining, spline broaching, and dual spindle operations. Its seamless part transfer, advanced tool paths, and intelligent automation allow manufacturers to achieve shorter cycle times, reduced setups, and higher overall precision in a single compact process. Metal cutting with an oxygen lance is a specialized process used for dismantling extremely thick or heavy metal components that cannot be separated by conventional cutting methods. In this scenario, the operation focuses on severing a massive cast iron shaft weighing 16 tons, requiring both skilled personnel and proper equipment to ensure safety and efficiency. Before the actual job begins, operators undergo dedicated training to understand the handling of the lance, the heat characteristics, and the necessary safety protocols. The procedure starts with preparing the oxygen lance holder, which secures the lance and provides stability for the operator. The lance itself is a steel tube filled with consumable rods that burn intensely when oxygen flows through at high pressure. Trained oxygen lancers position themselves carefully, maintaining the correct stance and grip on the holder. Once ignited, the lance generates an extremely high-temperature jet capable of melting and oxidizing thick cast iron. During cutting, the operator directs the lance along the predetermined line on the shaft. The reaction between the steel tube and the pure oxygen creates a continuous burning effect, producing a stream of molten metal that falls away from the cut. Despite the enormous mass of the shaft, the process is remarkably fast. The lance burns, on average, for 3.5 minutes, meaning operators must work with precision and speed while maintaining steady control. Throughout the operation, constant communication and monitoring are essential to maintain safety. By combining skilled training, proper equipment, and controlled use of the oxygen lance, the team successfully completes the cutting of the 16-ton cast iron shaft, demonstrating the effectiveness of this powerful thermal cutting technique. The assembly of an FCC reactor is a highly complex fabrication process that brings together massive components designed to withstand extreme temperatures and corrosive environments. Each reactor assembly can reach up to 70 meters in length, 10 meters in diameter, and weigh as much as 1,800 metric tons. Consequently, the process begins with the fabrication of large shell sections made from high-temperature chromium steel, often reinforced with stainless steel cladding to improve durability. After the shell is formed, the interior is fitted with a refractory lining that protects the structure during continuous high-temperature catalytic cracking operations. Next, internal components such as cyclones and the catalyst separation system are installed. These elements must be precisely aligned to ensure efficient flow and reliable reactor performance. Depending on project logistics, the reactor may be fully assembled at the fabrication yard, allowing all linings, internals, and external attachments to be completed before shipment. In many cases, the entire unit is transported as a single massive piece, ready for final installation. Alternatively, extremely large reactors may be shipped in multiple sections for field assembly, where specialized lifting systems and precise welding techniques ensure structural integrity and readiness for operation. The fabrication of an explosion-bonded clad pressure vessel begins with precise seam preparation. At each joint, the edges of the clad plate are carefully peeled back to expose the carbon steel backing material, ensuring access for welding. Next, the backing weld is performed, creating the primary pressure boundary that provides the vessel's structural integrity. Once the backing is fully joined, the clad restoration stage starts. A dedicated buffer layer of weld metal is first applied to prevent dilution between the high alloy corrosion-resistant cladding and the carbon steel substrate. After this protective layer is established, additional chemistry layers are deposited, each formulated to match the original clad composition and restore uniform corrosion protection. Depending on project requirements, several welding techniques may be employed during restoration, including SMAW, SAW, ESW, or FCAW, ensuring high-quality fusion and long-term service performance. The hot forming of heavy metal components, such as a thick hemi head, is a specialized forging process that transforms massive steel plates into precise, high-strength shapes. At ICEM WADA, this operation is performed on sections up to 125 millimeters thick, requiring extreme heat, carefully controlled deformation, and powerful forming equipment. The process begins with material preparation, where a cut-to-size steel blank is inspected and cleaned to remove scale or contaminants that might affect the forging surface. The blank is then transferred to a high-capacity furnace, where it is heated uniformly to forging temperature, typically above 1000 degrees Celsius. At this stage, the steel becomes sufficiently plastic and ready for shaping. Once the material reaches the required temperature, it is quickly moved to the forming station using heavy manipulators or cranes. The forging team must work efficiently to preserve heat, as temperature loss increases resistance and complicates deformation. The blank is positioned over a specially designed die set that defines the hemispherical profile. Using a hydraulic or mechanical press, the operator initiates gradual forming strokes, causing the heated steel to flow and conform to the die cavity. Because the hemi head is extremely thick, multiple forming passes are required. After each pass, the component may be reheated to restore plasticity and prevent cracking. Throughout the operation, skilled technicians monitor metal flow, temperature, and alignment to ensure uniform wall thickness and dimensional accuracy. Hammering, leveling, or intermediate shaping may be applied to correct distortions and guide the material into its final geometry. As the forging approaches completion, the part is pressed to its exact curvature and trimmed to remove excess material around the edges. The formed hemi head is then allowed to cool in a controlled manner, either in still air or inside an insulated environment, to minimize internal stresses. Following cooling, the forged component undergoes normalization or heat treatment to refine its grain structure and achieve the required mechanical properties. Non-destructive testing, such as ultrasonic inspection or dye-penetrant examination, is performed to verify internal soundness and detect any defects caused during deformation. Machining operations may also be carried out to prepare edges, nozzles, or weld bevels for subsequent assembly. Overall, the hot forming process enables the production of highly durable, stress-resistant metal components capable of withstanding extreme pressure and service conditions in industries such as petrochemicals, power generation, and heavy engineering. This method ensures excellent structural integrity and performance in demanding applications. The flanging and pressing processes are essential steps in forming precise metal edges and shaping heavy components. Two main machines are involved in this process: the flanging machine CIM FM30-6000 and the press machine CIM hydrogen phosphide. The flanging process begins with the flanging machine CIM FM30-6000, which is specifically designed to create consistent, accurate flanges along the edges of metal plates or cylindrical components. The machine can handle a wide range of thicknesses and diameters, providing the flexibility required for different industrial applications. The operator carefully positions the workpiece on the machine table, ensuring correct alignment and orientation. Using hydraulic or mechanical force, the machine gradually bends the edges of the metal upwards or outwards to form a precise flange. This operation improves the structural integrity of the component and prepares it for subsequent assembly or welding processes. The flanging machine is equipped with control systems that regulate the bending angle, speed, and pressure, ensuring uniformity across each part and minimizing the risk of deformation or cracking. After flanging, components requiring further shaping or deep drawing are processed on the press machine's CI-MHP 800, which delivers a maximum force of 800 tons. The press machine operates with high precision and stability, allowing it to form heavy-duty metal parts safely and efficiently. Components are placed onto the press bed, and the hydraulic system applies controlled pressure to achieve the desired shape, such as forming curved sections, embossing, or refining flanged edges. The combination of the CIM-FM 30-6000 flanging machine and the CIM-HP 800 press ensures that both light and heavy metal components are accurately formed, maintaining high quality and repeatability in production. Together, these machines streamline the flanging and pressing operations in metal fabrication workshops, reducing manual labor, increasing throughput, and enabling the production of complex, high-strength parts with precise dimensions. Their use is crucial in industries such as automotive, pressure vessels, and heavy machinery, where reliable and durable metal components are required. The heavy-duty press brake at real steel is capable of delivering nearly 1,000 tons of pressing force. In this demonstration, it formed a massive 6-meter-long, 16-millimeters-thick steel plate, showcasing the machine's extraordinary power and precision. This press brake, the largest in New Zealand, handles extreme workloads with ease. The video highlights the dramatic moment a perfectly formed part pops out of the tooling, captured in slow motion, emphasizing both the machine's strength and the quality of the finished component. The Bronneberg Super 3 scrap baler represents a proven and highly reliable solution for scrap processing, trusted by a multitude of satisfied users worldwide across a wide range of applications. Building upon the success of its predecessor, the Super 2, this baler combines robust engineering, operational flexibility, and user-friendly design to meet the demanding requirements of modern scrap businesses. At the heart of the Super 3 is a large, durable baling box, available with or without a front loader, allowing for efficient loading of various types of scrap materials. Its design incorporates fully serrated wear plates on 3 sides, ensuring long-term durability and resistance to the abrasive nature of scrap, while minimizing maintenance costs. This feature, together with its low-maintenance electro-hydraulic system, makes the Super 3 a cost-effective and dependable choice for any recycling operation. A standout feature of the Super 3 is its innovative shear function lid. Unlike conventional balers, the folding lid is equipped with integrated cutting knives that act almost like a scrap shear, slicing material during the compression process. This capability significantly reduces the need for pre-treatment of scrap, prevents blockages, and ensures smooth, continuous operation. The machine's low overall height and optional preloading box further simplify loading, making it accessible and easy to operate, even in constrained spaces. . The Super 3's hydraulic system is engineered for both power and precision. It employs a high-pressure electrohydraulic group with variable flow piston pumps, hydrological control valves, oil filtration, and an integrated oil heating and cooling system. All components are waterproof, ensuring reliable performance even in challenging environmental conditions. This sophisticated hydraulic setup enables consistent, high-quality baling, regardless of material type or site conditions. Flexibility is another key strength of the Super 3. It is capable of handling a diverse array of scrap materials, from large cutting and stamping remnants originating from production lines, to aluminum and steel turnings, beverage cans, and copper cable scraps. The baler's adaptable design allows for different packaging configurations, making it suitable for stationary or mobile installations, and eliminating the need for a concrete foundation. Operator convenience is central to the Super 3's design. The machine can be controlled via a remote control, and it features an automatic function for hands-free operation. This intuitive control system minimizes downtime, reduces the need for skilled operators, and enhances overall workplace safety. Even large or bulky scrap can be efficiently baled, reducing storage requirements and improving material handling for subsequent transport or recycling. Globally, the Bronneberg Super 3 has established a strong reputation for reliability, efficiency, and durability. Users in diverse industries, from steel and aluminum processing to municipal recycling centers, have consistently praised the machine for its ease of use, minimal maintenance requirements, and the high quality of the finished bales. Its robust construction, combined with a proven technical concept, ensures that the Super 3 continues to meet the evolving demands of the scrap industry with confidence. In conclusion, the Bronneberg Super 3 scrap baler is more than just a machine, it is a comprehensive solution for scrap management. Its combination of a shear function lid, rugged construction, low maintenance, and flexible operation makes it ideal for processing a wide variety of scrap materials efficiently and safely. Whether deployed in a stationary or mobile setup, the Super 3 delivers outstanding performance, operational simplicity, and reliability, reinforcing its position as a leading choice for scrap businesses worldwide. With this baler, companies can maximize productivity, minimize downtime, and achieve consistent, high-quality bale outputs, ensuring their recycling operations run smoothly and profitably.